Hi everybody, welcome to the next lecture on Multirate Signal Processing. This time we continue on filters. So last time we saw how to compute the frequency response. And now observe that the frequency response is symmetric around frequency 0 if we have a real valued impulse response. So to see why we get this symmetry, assume we change our normalized frequency omega to negative omega in our DTFT. So then we obtain this expression. So here we have our DTFT, but instead of having just omega, we now have minus omega, right? So now we can take a look at what happens with this expression, with this exponential. So if we change the sign of the exponent in this expression, it is equivalent to taking the conjugate complex value. So if we say e to the minus j omega, that's equal to e to the plus j omega conjugate complex, right? And here the overbar means conjugate complex. And you can easily see this using the Euler formula. So e to the j omega can be written as cosine omega plus j sine of omega, and if we take the conjugate complex of this expression, this is simply like taking changing the sign of the imaginary part. So this plus then results in minus, right? The plus turns to minus sinus. And then when you look at this expression, this is identical of changing the omega from plus to minus. Right? The cosinus is not changed going from plus to minus in the argument because it's an even function, but the sign of minus omega is a minus sign, right? So that's why the result is e to the minus j omega. So that basically shows this equation here, this equality. So now taking the conjugate complex means to change the sign of the imaginary part, and changing the sign of the complex exponential number means to rotate in the opposite direction, and this exactly corresponds to changing the sign of the resulting complex number. So now we take this result of changing the sign to the minus omega and also extend it to the rest of the sum, right? So remember, we also have the coefficients of our impulse response, h of n. And if h of n is real valued, then taking the conjugate complex does not change anything because the imaginary part is 0, right? So we can as well extend the conjugate complex over to h of n. And remember, this only works if h of n is real valued. And then we can as well extend it over the entire sum, right? And then basically the result is we have h of omega conjugate complex. So this is basically then this symmetry. Negative h of minus omega is identical to h of omega conjugate complex. Right, so this is true because the complex conjugate does not change the real valued numbers h of n. So it now shows the conjugate symmetry between negative and positive frequencies if we have real valued impulse responses. Right, and that's an important result. In summary, if we have real valued impulse responses or signals, the positive and negative frequency responses are conjugate complex of each other. Right? So basically we just need to have one half, say the positive frequencies from 0 to pi, and then the negative frequencies from 0 down to minus pi are basically obtained by taking the conjugate complex. Yeah, observe that this does not change the magnitude of our frequency response, only the phase. So if we take the magnitude of the conjugate complex frequency response, then it's the same because the magnitude of a complex number and the conjugate complex number is identical. Also observe that this symmetry is no longer true if we have complex valued impulse responses or signals. So if h of n is now also complex valued, then we cannot get the same result, right? Then those two halves, the positive and the negative frequencies, can be different. Yeah, so now to filters. Using frequency responses and the Z-transform, we can now analyze and design more general filters than just the running average or the running difference, which we saw last time. Applying a filter has the effect of multiplying the frequency domain description of a signal x of omega with the frequency response or transfer function of a filter h of omega to obtain the filter output y of omega. So in DTFT domain, we just multiply the two. So we have the frequency response of the signal x times the frequency response of the filter h, and that's the resulting output y. In the time or space domain, we get the corresponding operation by taking the inverse discrete time Fourier transform. Right? So we can just take this y, inverse transform it, and obtain the time domain result. Remember that a multiplication in the frequency domain becomes a convolution in the time domain. So this multiplication here in the frequency domain then turns into a convolution, which we see here. So the output of our filter is then x convolved with h being the impulse response of our filter. And this convolution, remember, is defined as this convolution sum. So the characteristic property of this convolution sum is that the sum index m here goes down on one of the two, here it's the signal, and goes up in the other argument. Right, so here we have it going down and here we have it going up. And here it goes from minus infinity to plus infinity. This is already what we saw for the example of the running average low-pass filter with a matrix formulation. But in that case, h was containing only two samples, so in that case, m would run from 0 to 1. Right? So this is now the more general formulation to obtain filters, which we can now use to design filters. So here an example. An ideal low-pass filter has a constant pass band with a constant magnitude of 1 and a constant stop band with a magnitude of 0. Right? So ideally, we want to pass frequencies in the pass band unchanged in amplitude and magnitude. And in the stop band, we basically want to multiply all the magnitudes in the stop band with a factor of 0 so that they are not passed through. And this is also called a brick wall filter because of the similarity of the magnitude of the frequency response with a brick. So here's the brick. So constant 1 in the pass band, and then all of a sudden here the brick ends, and then we have a factor of 0 in the stop band, right, from omega p to pi. So here pi again would be the Nyquist frequency. So we have now very easily designed this filter in the frequency domain. So this would be our filter goal, right? It's easy to wish for the perfect thing. We just need to know the pass band edge and the magnitudes of the pass band and the stop band. But usually we implement and compute our filters in the time or space domain, at least for short filters. This is more efficient to implement. So how do we obtain a corresponding impulse response? First, we also need to specify the phase, right? Because in a frequency domain, we have magnitude and phase. So we need to specify both. There are filters where we want to specify the phase, as in all pass filters. And there are filters where we don't care much about the phase, as in low pass example. If we don't care about the phase, we can give it an arbitrary value, like for instance 0. But there we find that we will get non-causal filters, so it makes sense to add a delay to make it causal, right? Meaning that it starts at time 0 and not before. In that case, we have a linear phase corresponding to that delay. So why is a delay a linear phase? We can write a delay by m sample points as multiplying the signal with z to the minus m in the z domain. Right. So here we see it. We have h, which could be our filter, and then we have the z transform of the filter as h of z. And if you multiply it by z to the minus m, then this basically gives it a delay by m samples. So we can also see this by looking at the z transform here in the next step. So this is the z transform. So here this z to the minus n comes from the z transform, and then this minus m comes from our multiplication. Then here we can use the index substitution, n prime equals n plus m. So then here in the exponent we just have this n prime as we should for the z transform, and now inside the impulse response we have this shift by minus m. So this is now the delay by m samples. So yeah, this is the z transform of the now delayed signal h of n minus m with a delay of m samples. So n needs to be correspondingly higher to get the same output. So in summary, a delay of m samples in the time domain corresponds to a multiplication with z to the minus m in the z domain. Observe that this delay can also be written as a convolution with the following impulse response s of n in the time domain. So here we see it. Here we have an s, and it contains almost all zeros. So here we have m zeros in the beginning, and then we have a 1, and then it continues with more zeros. Right? So as a convolution sum, we get this result. X of n convolved with s. This is our convolution sum, as we saw before. And here we see this s only has a value of 1 unequal of 0 at position L equals m. Right, so then what's left here is x of n minus m. So keep in mind here we start counting with 0. This is position 0, position 1, and so on, and this is position m. Right, so it's indeed a delay by m samples. And when we take the z transform of this operator s of n, then of course we get the same result. We see that the z transform is again here z to the minus m. So basically this confirms that a multiplication by z to the minus m corresponds to a delay by m samples. So this is to remember. A z transform element of z to the minus m corresponds to a time domain delay of m samples. And this is one of the fundamentals of multirate signal processing. So here a little example. We have now an IPython minus PyLab example. So let me open it. So here's already a little bit. So we have x, range of 1,5, and this gives us an array from 1 to 4, right? And then we have s. So s has a 1 at position 0, 1, 2, 3, so it has 3 zeros and then a 1. So this is our s, and then we can convolve the two, and then we can see that the resulting sequence is delayed by 3 samples. So let me plot it again here. Plot of x. Here's our signal x. And now plot of sx. And here we can see it's delayed by 3 samples. So now the first non-zero sample appears at 3. And this line here in between is basically an artifact from the plot function, which always draws straight lines between points. I could also say stem of sx to see the individual samples. So this makes it now more clear, right? So the first 3 samples are 0, and then the actual signal starts here with sample number 3. right? So here we can see this delay by 3 samples. Yeah, so now we can apply our trick to obtain the frequency response of a delay, right? So this is what we wanted to start with. We replace z by e to the j omega, right? Like last time. So the frequency response of this simple delay, capital S of omega, is simply e to the minus j m omega, right? So here, this is what's left from z to the minus m. Just plugging here instead of z, I have this e to the j omega, and this is the result, e to the minus j m omega. The magnitude of it is obviously 1, because the magnitude of e to the j something is always 1. And the phase is now what's behind the j, right? The phase is minus m omega. So it is linear in omega with a slope of minus m. Right? So this is now a function of omega, the phase, and it has this slope, minus m. And this minus m is constant. Right? So we have a linear function, and that's why it's called a linear phase. Yeah, in Python, we can plot the frequency response of our shift operator by using our frexy function of last time. So first we need to import SciPy signal. So let's do that, because that's where frexy is located. Then we can compute frexy, copy, paste. So now we have omega, the frequency, and h, which is our frequency response. And remember, we have an angle and we have a magnitude. So the magnitude here is not so interesting because we know it's constant 1. We can actually check abs of h. Indeed, we see many ones, so it's all ones, so that confirms it. So the more interesting part is the angle now, right? We want to know the angle of the delay operator. So copy and paste. So here we now see the angle. So you can see it. So horizontally we have the normalized frequency going from 0 to pi. And now you can see here we have a linear function. So we have, remember, we have a delay of 3 samples. So basically we have omega. So when we have 1, then we should have minus 3 for the phase, which indeed we can see here, right? So if I put my pointer here, we can see on the small numbers down here, 1 and minus 3. So indeed we have the slope of minus 3. And then shortly after, at should be precisely pi, 3.14, it jumps. And that's because the periodicity, the 2 pi periodicity of angles, right? An angle of minus pi is the same as an angle of plus pi. And that's why it jumps. It wraps around. So basically here, instead of going further down at pi, at minus pi, it jumps up to plus pi. So here we can see it's plus pi, and then it continues to go down until it reaches minus pi again, and then it will jump again. Okay. Yeah, so this periodicity of the angle basically makes those jumps happen. Yeah, so this is basically what confirms the linear phase. So now we know what to do with the phase. If we want to have causal filters, we need to have this delay with the corresponding phase. So how do we continue with the desired magnitude? Since we now have both parts, magnitude and phase, from the delay, we can simply apply the inverse discrete time Fourier transform to obtain the corresponding impulse response h of n. For our ideal low-pass filter, we obtain the well-known sinc function as our impulse response, because we have a rectangle in the frequency domain we will have a sinc function in the time domain. The two correspond to each other via the Fourier transform. So for the phase equal to 0 and for a desired upper limit of our passband omega p, we obtain the following. So this is the sinc function, still with phase 0, and with a width of our rectangle of omega p. So this is what we see here. So we have a sine of n omega p divided by n omega p. This is our impulse response, and this goes from n equals minus infinity to plus infinity. So we can see it's indeed not causal, right? Because it starts at minus infinity. So this makes the filter indeed non-causal, and it also, what's worse, it cannot be made causal because it would need an infinite delay. So this shows you that we have a problem here. This shows that it's not practically implementable, which is disappointing since it was a nice filter, right? This ideal brick wall filter. Okay, so how to fix it is then in the next part. So thanks for your attention and see you in the next part.